In the previous section, we talked about basic area and area of rectangles and squares. Today, we're going to talk about area of parallelograms and triangles. Again, the hope is you are familiar with these formulas, but in this class, we're going to take it further. The first thing, and this is super important, is this idea of the altitude of a figure. The altitude of the figure is the perpendicular height of our figure. So it's the perpendicular height, it's the distance from a figure's highest vertex perpendicular to its base, or we might also say its base extended, which I'll show you as we go through the day. So on a basic application, if I had a triangle, what we're used to seeing is that we think of the bottom being the base, and then we travel across to our top vertex, and we've done this many times this year. We drop a height down. We call this the altitude, or h for height. We'll use both. The big thing that I want you to keep in mind is that the bottom section does not have to be your base. We have three sides, and each of those could be the base. So let's say here, I'm going to real quick copy the exact same triangle. Let's say that I decided to call the current side that I'm marking the base. Well, if I'm going to draw the height to that specific base, I would travel across from that side to the vertex that's not connected to it and drop a perpendicular. And if I consider the side I now marked there, the base, this current altitude that I dropped is my height. The number might be different, but in all, it will keep the area of the figure the same. So the next up, we're going to move on to area of parallelograms and triangles. First theorem, our formula from here is the area of a parallelogram is equal to the product of the base of the parallelogram times the height. This gives us the formula that the area of a parallelogram, and I'll use that parallelogram symbol that we're used to, is equal to the base times the height. Now, the reason we did rectangles first is this formula is derived from a rectangle. That if I took a parallelogram, sketch one here real quick. If I took a parallelogram, and if I chopped off this piece here, and if I picked this piece up and dragged it, which will be difficult here, let's see if we can do it. If I picked this triangle up and I dragged it, it should be able to fit right here and forming a rectangle where the base is still the same and the height is still the same. So that's where our formula comes from. So for a parallelogram, what we're going to consider is that the whole length of the bottom will be the base. This diagonal is not my height. We've seen this a lot so far this year where we again need to drop an altitude, a perpendicular, and this would be the height of the parallelogram. Again, as we'll see later, I can draw the height. I can use this other side as a base, and I can draw the height this direction if we would like to. So it's flexible depending what side we call the base. So there is our parallelogram. It's base times height. Now, if I took a parallelogram, which I'll copy this one, and I were to slice it perfectly in half. So right down here. I want to know how this relates to a triangle. If I took this and I sliced it directly in half, well, here's what I know. The bottom is still the base. Nothing has changed. This here is still my height. But I've now sliced the figure in half. So if I only want half of the area, which now has formed a triangle, I know that with a parallelogram, if I draw the diagonal, it bisects my shape. It does cut it in half. So if I know how to find the area of the full figure using area is base times height, then we can derive the formula for the area of a triangle by taking the same parallelogram, slicing it in half to get the area of a triangle to be equal to half the product of the base times the height, which we are used to seeing with triangles. The area of a triangle is 1/2 its base times its height. So that's where our formula comes from. Real quick, before we move on to looking at a couple of problems, again, something that I want to point out is back up to my triangle here. Wherever I draw my base, as long as I go to the opposite vertex, I can draw a height the other direction. This is going to be important for us as we move forward. So let's look into a couple of examples. I'd encourage you to work through these because they show a couple of different pieces. If you understand area, again, you're welcome to try the problem set. Here's our first problem. We have a parallelogram given here. We have a side that's 13, the other side is 7. Remember, we do know opposite sides are congruent, so we know that the opposite side of 7 is 7, the other side is 13. Do we know the height? Hopefully, as you think through this here, you can figure out, no, the side that's 7 is not our height. So in this case now, I need to figure out a way to draw a height. Again, as we've talked about before, I could draw the height wherever I would like to draw it as long as it's perpendicular, but it makes the most sense to draw it to the intersection of my two sides. So I form a right triangle. I want you to take a minute. I want you to think about what type of right triangle we formed. Hopefully you notice this is a 30, 60, 90 right triangle. So remember with the 30, 60, 90 triangle, the ratios are very important. So if I have a 60-degree angle and a 30-degree angle, across from 30 is x, across from 60 is x root 3, and across from the right angle is 2x. So going back over to our diagram, this number that we know, 7, that's the 2x side. So that's twice my x value. So then if 30 is the top angle, I know that this side would be 7 over 2, or we could call it 3.5. And then to get the length of my altitude, I need to put a root 3 on that, which would make this in exact form 7 square root 3 over 2. I know this is not the prettiest number that we've seen, but it is an exact number. So now let's work with our area. Remember that the area of a parallelogram is base times height. So my base, the way I've drawn this, that the height connects to, is 13 units long. And my height is 7 square root 3 over 2. I'm helping you learn here how to keep exact numbers. So what I would do now is the 13 and the 7 are both in the numerator. So those can multiply together, and then we'll put everything over 2. So to keep it exact, 13 times 7 is 91. The root 3 comes along with that. And then the whole fraction, this is technically, the 13 is technically over 1. 2 times 1 is 2. So this gives us an exact answer of 91 root 3 over 2. You could also put this in your calculator to get it rounded to the nearest tenth, which the key has. So that's our first one. Often you will use special right triangles to find your altitude. That's a very common process. Next up, let's look here at number 2. Find the area of an isosceles triangle with legs of 41 and a base of 18. So let's draw our right triangle, or our isosceles triangle. We know that the sides are 41, 41, and 18. Remember that for a triangle, the area is 1/2 base times height. We could draw the height whatever direction we want, but it makes the most sense to drop from the vertex down to the base of 18 because in an isosceles triangle, it bisects it. So this makes my triangle set with a side of 9. The other leg is the hypotenuse, or is the altitude that we're looking for, and then 41 is the hypotenuse. So at this point, in order to find this, we know that we have a right triangle, and so this is where Pythagorean theorem could come into play. 9 squared plus h squared is equal to 41 squared. Now you can work the math through all the way on this, but to save us some time, this is a triple. It is a 9, 40, 41 triangle. So this means for us that h has to be 40. So now when I go back to my area formula, I have that the area is 1/2. Now, the trick with isosceles triangles is we're used to working with half the base. We still want to use the whole base, which is 18. So 1/2 of 18 times 40. And then from here, the 1/2 does not distribute. It only multiplies once. And so I usually if I can, start and multiply the 1/2 into one of them. So it becomes 9 times 40. You also could have done half of 40, but we just cannot do half of both. And this makes my area come out to be 360 units squared. All right, let's go on to the next one. This one will be very important. I would encourage you to watch through this example so that you'll understand bases. If you, again, feel like you get it partway through, you can move on. So here's the important part. They first ask us, they give us a parallelogram with lots of different numbers. What they're giving us is that this line AE, they're drawing it in as a height. What you want to think about is what base does it match with? And I'll use the highlighter to show this. AE is the height that corresponds when the base is BC. So if I knew the length of BC, which as I look here, I know will end up being 15 because it's a parallelogram, but I don't know the height. So I could, since I know the base and height, if I knew the area, then I could figure this out. But do we know the area? Unfortunately, we don't, so we're stuck. They also, though, gave us, interestingly enough, this 12. And the 12, it corresponds not to BC, but it corresponds to DC. If I knew both of those, I could use them to find the area. So what we know so far is the area of this parallelogram will be AE times 15. But we also know that DC is 10. So I also know that the area of the parallelogram is base of 10 times its corresponding height of 12, which is 120 degrees. Different base and height, same parallelogram. That means that these quantities, AE and 120, are equal. So that means for us here that 15 times AE has to equal 120. When we divide here, that makes AE come out to be 8. So if you can figure out the area using another base and height, it allows us to go back and find a height. That's kind of the lesson that's shown here. All right, so we got the first part. We got part A. Now let's go back. It asks us to find the ratio of x to y, meaning I just need to know how long they are. So what do we currently know? I don't see they're a part of any specific right triangle. It might make it more complicated, but I do see I have this piece right here, BE, and I have this piece DF, and that is a part of a right triangle that I know a fair amount about. I just figured out that AE was 8. I want you to think, do we recognize this triple? Something 8, 10. That will make this a 6, 8, 10 triangle, which would make x have to be 15 minus 6, which would be 9. And then next up, something 12, 15, that's a 3, 4, 5 times 3, which would make this DF 9. And then 10 minus 9 is 1. So then that means that x is 9, y is 1, giving us a ratio of 9 to 1. Alrighty, here we go. Last one. In this triangle here, they tell us that AR is congruent to AG, and they're both 20 millimeters. And then they tell us angle A is 40 degrees. So this angle here is 40 degrees. So at some point, I have to draw in a base, and I have to draw in a height. So you could choose to draw this in however we want. You could choose to draw your height to 20 and figure that out, or you could choose to draw your height through. It doesn't matter, but let's say that we choose to go this direction. If I choose to draw my height this way, currently I know a couple of things. I know that as I look at it, the base is 20, and then the height is this blue piece that we don't know. It's unknown. But I also know that this angle here is 40. And there is a right triangle formed with this. What you want to start thinking about is trigonometry, or our SOHCAHTOA. we can use this angle to figure out the height, although we don't have enough information to do Pythagorean theorem. So in reference to AR is the hypotenuse. This little piece right here is the adjacent. And then my height that I'm looking for is the opposite. So looking over here with SOHCAHTOA, I have an unknown on O and I know H. So that would mean here that I could say that the sine of 40 degrees is equal to H over 20. So that means for us here that H is equal to 20 times the sine of 40. All right, now let's put this in the calculator. So if I'm using Desmos right now, and if you're looking for the trig functions, we go functions sine 40. Now I just want to make sure if you click the arrow, I am in degrees, so that's good. So my answer, they want the nearest hundredth, so let's go more than that. Let's go one more. That would give us a height of 12.856. So now I have all I need. My base is 20, my height is 12.856. So that means with this triangle, the area is 1/2 of base, which is 20, times 12.856. Now, you could choose to put this in your calculator all in one line, or you can break it down. This makes this 10 times 12.856, which makes this 128.56. And the units they gave here, and so that's going to be millimeters squared. All right, that is it. As a quick reminder, parallelogram is the base times the height. For a triangle, it is 1/2 base times height. Remember, the height can come in many different places depending on what base we're talking about. That is it. Next up is the 11.2 practice.